So this is an experiment I've been meaning to do for a while. I've had this artificial horizon for quite some time. I purchased it on eBay and it's out of a Bell helicopter. It's a fully functional, electrically operated artificial horizon. And I'll just show you that it's designed to be mounted on a 5-degree tilted panel. So basically sitting on the table, it's going to be close enough to that. And I'll list all the specifications in the comments for this video. Now, this artificial horizon, being electrically operated, I've just got some wires that I've connected there this afternoon, and I'm going to power it with this LiPo battery from one of my large drones. It's up to 25 volts, so it's not quite the operating specification for this artificial horizon, but it does power it fast enough for it to be fully functional. Now, what I'll do in the future is I'll get a dedicated 28 volt lab power supply. The one I've got at the moment only goes up to 16 volts, but I will get a dedicated unit for this for further experiments. So this is just the first demonstration of the artificial horizon and how it works. Now, the artificial horizon is presently unpowered and it has this knob called a caging knob. Now, it won't really achieve anything when the artificial horizon is not powered, but when it's powered, by pulling the knob out, it centers the gyro in roll and pitch. So the way I'm going to do this experiment is power up the gyro, and then I'm going to cage the gyro and rotate it 20 degrees and release the cage. Now you'll see that when I put the gyro back to level, the gyroscope will be angled off to the side, and what we're then going to do is time to see how long it takes for the gyro to correct back to level. And what we're looking for here is the self-alignment properties of the gyroscope. Does the gyro have self-correcting mechanisms that will constantly keep it aligned to level? This is an aircraft artificial horizon and it's a self-alignment experiment. Now, flying in a jet aircraft at 450 knots, the attitude of the aircraft changes by 1 degree every 8 minutes as it cruises across the curvature of the Earth. Now, the purpose of this demonstration is to see, firstly, if the gyro does self-align, and secondly, does it self-align faster than 1 degree in 8 minutes? Because if we can determine that this gyroscope is in fact correcting itself faster than 1 degree in 8 minutes, it will explain perfectly why it appears to stay level as an aircraft is cruising across the Earth and moving around the curvature, because the gyroscope is constantly correcting itself. And this experiment will either prove or disprove whether this gyroscope has correcting mechanisms and whether it can actually correct at a rate of 1 degree every 8 minutes or faster. So we're now going to connect power, and you will hear the gyro speeding up, and there's a couple of things I want you to notice. Presently it's unpowered. If I pull the caging knob, have a look at the attitude, and also note this small red off flag. Now that flag displays when the gyro is not receiving sufficient power. So you'll see that when I do connect power, this flag disappears, and that is evidence that the gyro is receiving sufficient power to operate normally. So let's just connect power. You can see that the off flag has disappeared. You can probably hear the gyro spinning up, and you'll see that it will slowly align itself to level. So the gyro is now aligned nicely, and what we're going to do is the first demonstration where I will deliberately put the gyro out by 20 degrees and we can time how long it takes to self-correct. And let me just show you first that the gyro is actually working. If I move the case, the gyro inside the artificial horizon is holding level nicely. If the aircraft were to pitch up, that's the indication you get. If the aircraft pitches down, that's the indication you get. The aircraft is banking to the right. It looks like that. The right wing is low. If it's banking to the left wing is low. So the artificial horizon is functioning correctly. So now what we're going to do is cage the gyro. I'm going to rotate about 20 degrees to the right. I'm going to release the cage and then put the case back, and you'll see it's just a little bit more than 20 degrees misaligned now. So I'm going to start the stopwatch and we'll see how long it takes for the gyro to erect itself back to level. Now, as you can see, it is definitely in the process of realigning itself. It's only been going for less than 2 minutes, and it has already corrected by more than a couple of degrees. Just to explain, this is the vertical position. The first white mark is 10 degrees bank. The second one is 20 degrees bank. And the third one there is 30 degrees bank. The little white dot is 45 degrees bank, and the next white line is 60 degrees bank. So when I deliberately offset the gyro, it was just more than 20 degrees, and you can see now it has reduced to about 17 degrees angle of bank in just 2 minutes. So it's definitely correcting itself much faster than 1 degree every 8 minutes. We'll just let it run until it's completely wings level again, and then we'll repeat the experiment, rotating it in the opposite direction. You can see now the artificial horizon is showing just 10 degrees angle of bank, so it has already corrected more than 10 degrees in just 5 minutes. Remember, it only needs to correct 1 degree in 8 minutes to be able to compensate quite easily for the movement across the Earth's curvature in a jet aircraft. This is correcting much faster. It has corrected more than 10 degrees in just 5 minutes. So there's the 8-minute mark. The artificial horizon is now showing about 5 degrees angle of bank, which means in 8 minutes it has corrected more than 15 degrees of error. Now that is far more capable than what is needed just to correct 1 degree every 8 minutes. In fact, this humble little gyroscope out of a helicopter would function perfectly on something traveling as fast as the SR-71. It's correcting fast enough to easily compensate for the curvature of the Earth, even in an aircraft that fast. So coming up to 10 minutes, it's basically back to wings level. So we'll stop the stopwatch there. Reset. I'll just reset the video. So I've just started the video. This time we're going to offset the angle in the other direction, just to confirm that it wasn't a fluke. So pulling the cage knob, rotating the opposite direction this time, releasing the cage knob, and putting the gyro back on the table. Now you can see we've almost got 30 degrees of error there. So let's start the stopwatch and see how long it takes to come back to wings level. You'll notice also there's a small degree of nose up. Let's see if the gyro corrects that as well. You can see in just 4.5 minutes, it has corrected most of that 30-degree angle of bank error, and it is now correcting the pitch error as well. So as you can see, in less than 8 minutes, it has corrected 30 degrees of error. It only needs to correct 1 degree in 8 minutes to be able to correct for the curvature of the Earth at 450 knots. And the final part of the experiment is just adjusting the pitch and seeing if it will correct the pitch only. So I'll stop the stopwatch. We'll reset the video. So the reason I stop and start the video is just in case I say something incorrect. I only have to repeat this section of the video, not the entire length. And as it turns out, it was fortuitous because the phone just ran low on battery and stopped halfway through the last demonstration. So I've just plugged it into the charger and we will repeat the demonstration. And this part is just to show that it will correct in pitch. So what we're going to do is just cage the gyro. We're then going to pitch the aircraft upwards by about 10 degrees. I will release the cage and then lower the attitude. So that's now indicating about 10 degrees nose down. And if we start the stopwatch, let's see how long it takes for this gyro to correct back to level. Remember, it only needs to correct 1 degree in 8 minutes for an aircraft traveling at 450 knots. So let's see how long it takes to correct 10 degrees. So there you can see in just 5 minutes it has corrected itself back to the level attitude. So it's easily correcting 10 degrees in 8 minutes. It only has to correct 1 degree in 8 minutes. And in case you're wondering why it's not showing perfectly wings level, it's because this table is not perfectly level. And just to prove that, I've put a small bubble level on top of the artificial horizon, and you can see that the bubble is just there. So the body of the artificial horizon is not perfectly level there, and that accounts for that very slight angular difference. If I just tilt it so that the bubble level is level, the bubble level is level now, you can see the wings are perfectly level also. So we'll just remove power now, and you can see right away that off flag reappears, indicating the gyro does not have sufficient power to operate correctly. And you can also hear the gyro speed winding down. Now this demonstration is absolute proof that the artificial horizon in an aircraft has self-correcting mechanisms that will rapidly correct errors in roll and pitch back to level. It was correcting at the rate of more than 10 degrees per 8 minutes. Now, flying in a jet aircraft at 450 knots, it is only required to correct at the rate of 1 degree in 8 minutes. So this small electrically operated artificial horizon can easily compensate for the curvature of the Earth. It can continue to show a level attitude as the aircraft is moving across the Earth and changing its attitude as it follows the curvature of the Earth. 1 degree in 8 minutes is all that is required. We have just proven that this artificial horizon can correct at a rate much greater than that. So this demonstration should put to rest once and for all the flat Earth claims that the artificial horizon in an aircraft proves the Earth is flat. It does nothing of the sort, because the artificial horizon has self-correcting mechanisms. So in the future, if you have any flat earthers tell you that the aircraft artificial horizon proves the Earth is flat, please direct them to this video, because we have just demonstrated the self-correcting mechanisms. Now this is part 1. I will be doing further demonstrations, and when I have completed all the demonstrations with this gyro, I will do a video disassembling the unit and showing you how the correcting mechanisms actually work.